In the last couple of videos, we got a taste for what happens when things change, when the current changes abruptly. Up until this point, we've been dealing with DC circuits, direct current circuits. Our source of potential difference, our power supply, provides a constant potential difference, a constant voltage, and that keeps current flowing in the same direction through the circuit the whole time and at the same rate. Well, that's true once the circuit's been hooked up for a little bit of time. As soon as things come to a steady state, which happens in 100 milliseconds or so, the current stays constant, it stays moving in the same direction because our potential difference is constant and always pushing the electrons in the same direction through the circuit. When we talk about AC circuits, alternating current circuits, our power supply, our source of potential difference, is flipping back and forth. It creates a potential difference in one direction, pushing charges in one direction, and then it reduces and flips and creates a potential difference in the other direction, causing the charges to go in the other direction. So the charges move one way, come to a stop, move the other way, come to a stop, and they move back and forth like that through the circuit. And because of this changing current, things like capacitors and inductors behave very differently in an AC circuit as they do in a DC circuit. In fact, they even behave differently as the frequency changes that we're changing our power supply. We can change our power supply to flip at a fairly low frequency, or we can change it so it's reversing very quickly at a very high frequency. And capacitors and inductors behave differently in those situations. So let's take a look at resistors, capacitors, and inductors in AC circuits in a little more detail. This symbol is for an AC power supply. The voltage it produces changes in time according to a sine wave, typically. We could also have something that produces a square wave or a sawtooth wave or something like that. But in most of our circuits, we deal with potential that's changing as a sine function because that's what we get delivered to our house. We know that for a resistor, V is equal to IR. And if we wanted to know how does this change, how does that resistance change as we change the frequency? So I've got my power supply turned way down to a frequency of 0. What does that mean? That means it's not changing at all. That means it's just a DC power supply. What is my resistance of my resistor? It's just R. As I turn it up a little bit so that that power supply now is flipping voltage, maybe it flips once every second, the resistance of that resistor is still R. Its effect on the flow of charges through the circuit is still the same. And then I increase my frequency so it flips 5 times every second. The resistance still has the same effect on the flow of charges. Now I flip it 50 times every second. It still has the same effect. The resistor's effect on the charges moving through the circuit does not depend on the frequency that their power supply is switching. It's independent of the frequency. The resistor always has a resistance R, and it always has the same impact on the charges moving through the circuit. The resistor hinders the motion of the charges. It makes it more difficult for those charges to move through the circuit. Let's take a look at a simple circuit with a capacitor in it. We know that that capacitor is really an open circuit. When we hook up a capacitor in a circuit to a battery or a DC power supply, for a very short period of time, charges move until the charges build up enough on those plates to push back and prevent any more charges from moving through the circuit. And that capacitor is really an open circuit. So it acts like an infinite resistance because no charges can move after a certain amount of time. But if we change the frequency, we can get charges to move through this circuit, not through the capacitor, right? They'll never move through the capacitor. That's an open circuit. But what is that capacitor? It's like a reservoir. It can hold charges. So we can get charges to move in one direction. When this side is higher potential than that side in my power supply, I can get charges to flow such that we start to build up some positive charge here. And as those charges build up, it becomes harder and harder to flow more charges because they resist. They don't want any more charges to build up on that plate. So to push the next two charges on there takes a little bit more effort and takes a little bit more time and slows things down. So the capacitor, while it's charging up, acts kind of like a variable resistor. It acts like a resistor whose value is increasing in time. Then, if we wait long enough, it will act like an infinite resistance and push back so hard we can't flow any more charges and the current basically goes to zero. But then we can flip the potential on our power supply. That's what happens in an AC circuit. And now current is flowing this way. And so the positives start to build up on the lower plate. And the first ones flow very easily. And then it starts to get harder and harder. But what would happen if I made that frequency switch faster and faster and faster? Well, as I start to flow charges, let's say the potential is the way it is here, the bottom of my power supply is positive, a few charges start to flow. And before they can build up and really push back and have an effect on the flow of charges in the circuit, I flip the potential on my power supply, and now they flow in the opposite direction. And before they can build up enough where they impact the flow of charges, I flip again. You see what I'm getting at? It's almost like it's not there. It almost has no effect at all on the flow of charges through the circuit if I'm changing the power supply fast enough. If I'm flipping the potential on the power supply fast enough, it almost has no effect on the flow of charges. And the slower I flip the power supply, the more of an effect it has on the charges moving through the circuit. It hinders the flow of charges moving through the circuit, kind of like a resistor. But we don't call it resistance because it's a very different mechanism here. Resistance occurs because the electrons moving through the conductor collide with the atoms and molecules that make up the conductor, and that hinders their motion. And that's what we call resistance. In this case, that's not the mechanism at all, but it has a similar effect. But because it's a different mechanism that hinders the flow of charges through the circuit, we don't call it resistance, we call it reactance. So it's very much like resistance as far as the flow of charges is concerned. It's just a different mechanism. We use this symbol chi, the Greek letter chi, or X if you prefer. And we have capacitive reactance. That's the subscript C there. This is for a capacitor. And what would that depend on? Well, I already told you. The faster this thing switches, the higher the frequency, the less effect the capacitor has on the flow of charges through the circuit. So its reactance has to get smaller when the frequency gets bigger. It's an inverse relationship. And the other thing it would depend on is the capacitance. The larger the capacitor, the more charges can build up on it before it starts to push back and have an effect on the circuit. So the capacitance also has an inverse effect. So our reactance is 1 over omega c. Omega is the frequency, the angular frequency that the power supply is flipping. Remember that the voltage here is V max times the sine of omega t. So omega is our angular frequency of oscillation. And how do we convert that to F, our frequency, or the number of times it flips per second, the number of cycles per second? Omega is equal to 2 pi radians per cycle times the frequency, which is cycles per second. So if we plot our reactance versus the frequency, and we can, doesn't matter whether it's omega or F here, we get the same shape. We know that this has to go to 0 as the frequency goes to infinity. It has almost no effect on the circuit as the frequency goes to infinity. And it has to go to infinity as our frequency goes to 0, because we know it acts as an open circuit for a DC power supply, a 0 frequency source. So we get a curve that looks something like this, 1 over omega c. Let's think about what happens in an inductor now. We know that as things change, when the current through the inductor is changing, it creates a changing magnetic flux through that coil. That changing magnetic flux causes the inductor to push back to resist the change. If we're trying to increase the current by pushing it clockwise through the circuit, then the inductor tries to push current in the opposite direction. It fights us and it makes it hard to get the current to flow. It acts like a resistance to the flow of current, but it's not a resistor. It has what we call reactance. It opposes the flow of current. So when things are changing, has a big effect. It pushes back hard and really impedes the flow of charges through the circuit. But when things aren't changing, when this is just hooked up to a battery, it doesn't have any effect on the circuit. It's like a wire there, a 0 resistance path for current to flow when things aren't changing. So let's take a look at what the formula is for reactance. We know it's going to increase as the frequency increases, and it's going to increase as the inductance increases. So it's just equal to omega times L. And what happens when we plot the reactance versus frequency? As the frequency goes to infinity, we know the reactance has to go to infinity. It has to act like an open circuit. And when the frequency goes to 0, the reactance has to go to 0. It acts like a short. Let's take a look at this circuit in 2 extreme cases. One, when the frequency goes to infinity, and one, when the frequency goes to 0. So let's do the frequency going to infinity first, the high frequency limit. So in the high frequency limit, when the frequency F or omega goes to infinity, what does a capacitor act like? A capacitor acts like a short, a 0 resistance path. And what does an inductor act like in this limit, the high frequency limit? It's just the opposite. It acts like an infinite resistance, like an open circuit. So let's redraw the circuit. Our resistor doesn't change. Doesn't matter what the frequency is, the resistor just acts like the resistor. But this inductor I can take out of the circuit. And the capacitor I can replace with a wire. It just acts like a short. And on the other side, I can replace this capacitor with a wire, and this resistor acts the same. And my circuit looks like this. I could draw it one more time. Two resistors in parallel. If this has a resistance R and this has a resistance R, then this would be R over 2. So the circuit looks like it has a resistance of R over 2 in this high frequency limit as the frequency goes to infinity. Now let's take a look what the circuit looks like when the frequency goes to 0, the low frequency limit. What does that mean? It's like we're hooking it up to a battery, a DC source. Our capacitor now looks like it has infinite resistance, and our inductor acts as a short. So we can redraw this circuit. The resistors still look the same. But the capacitor acts like an open circuit here, and the capacitor up here acts like an open circuit, and our inductor acts like a short. So now our circuit looks not like two resistors in parallel like it did before. Now it looks like two resistors in series. So I could redraw this as an equivalent circuit with a resistance of 2R. So as we're changing the frequency that's being delivered to this circuit, the resistance of the circuit appears to change. In one case it's low, in the other case it's 4 times higher. Why is this advantageous? Because we can make filters now. We can make a circuit that looks like very low resistance to one frequency, but very high resistance to another frequency. And we can filter out noise in our signals. A simple example would be if you have your power lines in your house, they run at a very low frequency, 60 hertz. The power cycles 60 times every second. But audio and video signals have much higher frequencies. And if you have those wires running right next to your electrical lines in your walls, they might pick up some noise. So you could run your signal, your audio signal, through a high pass filter that would not allow, it would look like a very high resistance to that 60 hertz. It would not allow that to pass through, but it would allow your audio signals, your high frequency audio and video signals, to pass through no problem. And there are lots of applications like that, where you would want to have a high pass filter or a low pass filter, or maybe try to make it where a certain band of frequencies in the middle passes through, but everything else doesn't. So filters are an interesting application in circuits where we use this phenomenon.